Download this code from codegive.com, link in the description below. OK, let's delve into the world of complete information game theory, covering its core concepts, practical examples, and Python code illustrations. This will be a comprehensive guide to help you understand and apply these principles. What is complete information game theory? Complete information game theory is a branch of game theory where all players have full knowledge of the set of players, the set of possible actions, strategies, available to each player, the order of moves, the payoffs, utilities, associated with each possible combination of strategies. In simpler terms, everyone knows the rules of the game and the potential consequences of every action. This contrasts with incomplete information games, where at least one player lacks perfect knowledge about some aspect of the game. Key concepts. 1. Players * the decision-making entities involved in the game. Each player aims to maximize their own payoff. 2. Strategies * a complete plan of action for a player. It specifies what the player will do in every possible situation, even if some situations are never actually reached. * Pure strategy * a player chooses a single action with certainty. * Mixed strategy * a player chooses actions with probabilities. 3. Payoffs * the numerical value, utility, a player receives for a given outcome of the game. Payoffs represent a player's preferences. 4. Game representation * games can be represented in different ways. Normal form, strategic form represented by a matrix that shows the players, their strategies, and the payoffs for each possible strategy combination. Suitable for simultaneous move games. Extensive form, tree form, a tree diagram that shows the sequence of moves, the players making the moves, the information available at each decision node, and the payoffs at the terminal nodes. Suitable for sequential move games. 5. Solution concepts * methods for predicting the outcome of a game, based on assumptions about player rationality. The most important solution concept is Nash equilibrium * a set of strategies, one for each player, where no player can improve their payoff by unilaterally changing their strategy, given the strategies of the other players. It's a stable state where no one has an incentive to deviate. Types of complete information games. Static games * players choose their actions simultaneously, without knowing the actions of other players. Example: The Prisoner's Dilemma, Rock Paper Scissors. Dynamic games * players move sequentially, with some players having information about the previous moves of other players. Example: Chess, Ultimatum game. Finding Nash equilibria. Dominant strategy equilibrium * a strategy that is always the best choice for a player, regardless of what the other players do. If all players have a dominant strategy, then the combination of these strategies forms a dominant strategy equilibrium, which is also a Nash equilibrium. However, dominant strategies don't always exist. Iterated elimination of dominated strategies, i.e.s. if a strategy is always worse than another strategy, regardless of what the other players do, then it is strictly dominated. IEDS involves repeatedly eliminating strictly dominated strategies until only one strategy remains for each player, or until no more dominated strategies can be found. The remaining strategies form a Nash equilibrium, if a unique set remains. Best response analysis * for each player, determine the best strategy to play for each possible strategy of the other players. A Nash equilibrium occurs when all players are playing a best response to the strategies of the other players. This often involves finding the intersection of the best response curves. Asterisk mixed strategy Nash equilibrium asterisk when players randomize over their strategies. To find a mixed strategy Nash equilibrium, you need to determine the probabilities that make each player indifferent between their pure strategies, given the probabilities of the other players. Examples of complete information games. 1. Prisoner's dilemma asterisk. 2 suspects are arrested for a crime. They are interrogated separately. Each suspect has the choice to cooperate with the other, remain silent, or defect, betray the other. The payoffs are as follows. Suspect 2 cooperates, Suspect 2 defects. Suspect 1 cooperates, -1, -1, -3, 0. Suspect 1 defects, 0, -3, -2, -2. Asterisk the numbers represent, Suspect 1's payoff, Suspect 2's payoff. Asterisk dominant strategy asterisk defecting is a dominant strategy for both players. Regardless of what the other suspect does, a suspect is always better off defecting. Asterisk Nash equilibrium asterisk, defect, with payoffs of, -2, -2. This is a Pareto inefficient outcome, as both players would be better off if they both cooperated, -1, -1. 2. Battle of the sexes asterisk. A couple wants to go out, but they have different preferences. One prefers going to the opera, while the other prefers going to a football game. They both prefer to spend the evening together rather than going alone. Wife, opera wife, football. Husband, opera, 2, 1, 0, 0. Husband, football, 0, 0, 1, 2. Asterisk Nash equilibria asterisk, opera, and, football, There's no dominant strategy. 3. Matching pennies asterisk. 2 players simultaneously choose to show either heads, H, or tails, T. If they both show the same side, player 1 wins. If they show different sides, player 2 wins. Player 2, H. Player 2, T. Player 1, H, 1, -1, -1, 1. Player 1, T, -1, 1, 1, -1. Asterisk no pure strategy Nash equilibrium asterisk there's no combination of strategies where neither player has an incentive to switch. Asterisk mixed strategy Nash equilibrium asterisk both players randomize, choosing H with probability 0.5 and T with probability 0.5. Python code examples. We can use libraries like NashB to analyze and solve games represented in normal form. Explanation of the code. 1. Import NashB asterisk this line imports the NashB library, which provides functions for creating and analyzing games. 2. Define payoff matrices asterisk. Asterisk A represents the payoff matrix for player 1. The rows correspond to player 1's strategies, and the columns correspond to player 2's strategies. Asterisk B represents the payoff matrix for player 2. Asterisk important asterisk NashB assumes that the rows correspond to player 1's strategies and the columns to player 2's strategies, so the payoffs in B are indexed the same way as in A. 3. Create a Nash.game object asterisk Nash.game, A, B, creates a game object from the payoff matrices. 4. Find Nash equilibria asterisk. Asterisk prisoner underscore dilemma dot support underscore enumeration. This function attempts to find all Nash equilibria using support enumeration. This method works well for small games, like these examples. For larger games, other algorithms might be needed. 5. Print the equilibria asterisk the for loop iterates through the found equilibria and prints them. Each equilibrium is represented as a tuple of probability vectors, one for each player. For example, np.array 0, 1, np.array 0, 1 means player 1 plays the first strategy with probability 0 and the second strategy with probability 1, i.e., they always play the second strategy. Player 2 does the same. Important notes on using Nashby *** payoff matrix structure * ensure you construct the payoff matrices A and B correctly. Rows represent player 1's actions, and columns represent player 2's actions. Double-check your payoff values to avoid errors. Game size * support enumeration can be computationally expensive for larger games with many strategies. Consider using other algorithms, like Lemke-Hausen for 2-player games, for larger games. Mixed strategies Nashby provides tools for finding mixed strategy Nash equilibria. Install Nashby You'll need to install the Nashby library before running the code. Pip install Nashby. Beyond basic examples. Sequential games For games with sequential moves, you would typically use the extensive form, game tree, representation. Finding Nash equilibria in extensive form often involves backward induction. Nashby primarily focuses on normal form games. For extensive form games, libraries like Gambit are more suitable, but they have a steeper learning curve. More complex payoffs The payoffs can be more complex than just simple numerical values. They could be functions that depend on external factors or player beliefs. More than 2 players Nashby can handle games with more than 2 players, but the complexity of finding Nash equilibria increases significantly. Summary. Complete information game theory provides a framework for analyzing strategic interactions when all players have perfect knowledge of the game's rules, strategies, and payoffs. Understanding key concepts like Nash equilibrium, dominant strategies, and game representations is crucial for applying these principles. Python libraries like Nashby can help you model and solve simple complete information games, but remember to choose the right tools based on the complexity of the game you are analyzing. This tutorial has given you a good foundation. Practice with different examples, and explore the resources and libraries mentioned to deepen your understanding.